Hello, welcome back. Okay, modern radiation therapy planning and then the delivery system, the whole goal is this. Okay, how do we maximize the dose to the target at the same time while minimizing dose to the normal tissue? So I'm not sure you guys actually have seen this graph. It's called TCP and NTCP. So look at TCP first. Okay, TCP stands for tumor control probability. Okay, so tumor control probability. So at the low dose, your chance of controlling the tumor will be zero, right? But as you increase the dose, your chance of killing the tumor will increase. Okay. But what is NTCP? NTCP is normal tissue complication probability. Okay, so that means the complication probability of normal tissue will also increase. So as you increase the dose, you're not only killing the tumor, you have this collateral damage of normal tissue. Okay, so normal tissue complication rather, probability also increase. So our goal of treatment planning optimization and then delivery is this how to separate this gap. Okay, so by separating this gap, we can find some dose where we can, control the tumor while minimizing the dose to our normal tissue. Okay. So what are the method of separating these two? Okay. Today's lecture, we're going to talk about IGRT basically. Okay. Imaging during the delivery. So one of the modern treatment delivery technologies, IMRT, right? Intensity modulated radiation therapy. So the goal is we want to deliver target dose to target, with very steep dose gradient. Okay. So for example, we have some tumor, head and neck tumor, and then you have this, maybe this is PTV high and PTV low. PTV high is getting 66 gray, and PTV low, they have two different PTV lows. Okay, PTV mid rather 60 gray, and PTV low is getting 54 gray in this example. And then what do we have? We have this priority glands, right? So the plan is optimized in a way that will deliver very, very high dose to the target, primary target, and then you have this ipsilateral target is getting 60 and contralateral target is 54. And then at the same time, you want to minimize those to the parotid gland. So you end up having very, very steep dose gradient across these two different organs of interest, right? So if your plan is this fancy, the accurate target localization during the delivery is also very, very important, okay? So however you fancy your plan is, if your delivery is off by, say, 5 millimeter, you are risking either underdosing the target or overdosing the OAR. All right, so let's talk about the set of uncertainty, okay, or like daily target localization uncertainties. So first, we'll talk about inter-fractional error, and then next slide, we'll talk about intra-fractional error, okay? So what are the changes in target position between the fractionated fractionated treatment rather. So that means actually for a given day, a daily patient set of error, right? So such as target deformation, or like tumor shrinkage or tumor swelling, and different filling of stomach or rectum. Okay, so in this example here, you're looking at head and neck treatment of daily CT, daily cone-beam CT. Now I think it's daily MBCT of tomotherapy. So you might have noticed that the patient is losing weight. Okay, so given day, the patient, as the number of fraction increases, the patient is losing weight. Okay, 1 through 35 fraction. So that is considered as interfractional error. On your right, you have prostate treatment. Again, this is daily MBCT, tomotherapy unit. So daily alignment is done with this fiducial marker. So the fiducial marker stays in the middle and then set up very, very nicely. But this patient's rectum filling was not very well controlled. Maybe it's not that bad, but but there is a change day to day, right? So in our department, we do full bladder and empty rectum, but in this example, it looks like it's not very well controlled. But anyway, these are categorized as interfractional error. Okay, then what are the intrafractional error? Intrafractional means the changes in target position during a given fractionated treatment, such as breathing motion, lung tumor, for example, or liver tumor. It moves up and down, right? Unless we control the breathing. So that is categorized as intrafractional error. Okay, and also such as like moving gas inside the intestines, and some patients who are not cooperative, they tend to move. That can be categorized as intrafractional error. So the in-room imaging can help significantly reduce this interfractional motion or interfractional set of uncertainty. Okay, day-to-day set of uncertainty. Okay, so you can identify the additional couch shift every day. If we think about cone-beam CT, we take cone-beam CT and then we apply the shift, and that shift is for that fraction specific, right? So every fraction we take cone-beam CT and then we apply the shift, right? So we can monitor the tumor response over time, interfractions, and this image of daily cone-beam CT can be used for delivery dose verification. Okay, but in-room imaging is not only for the interfractional. Our department, what do? We detect fluoro, right? Fluoro. Okay, so the fluoro image that we take during the treatment will help intrafractional, right? So it's not just inter or intra, but mostly our in-room imaging, the goal of in-room imaging is interfractional motion, interfractional set of uncertainty reduction. Okay, so I've shown you this slide before in my first class. So these are the commercial solutions for the in-room imaging. So as we all know that we have Varian OBI system, and that it can be a CT on rail, or like V-Ray system uses MRI. Then Electa Synergy, this is very similar to Variant solution. It has MV and KV. And then tomotherapy unit has megavoltage CT rather. Okay, and CyberKnife has this ceiling mounted X-rays. And then you can create, I don't think it cannot capture 3D image, but it can still get oblique 2D shots, okay, as many as needed. Well, let's talk a little more about cone beam CT. Okay, it utilizes cone-shaped X-ray beam. Okay, this is X-ray source, and this is you're seeing the back of the actually imaging panel, and then the cone beam CT looks something like this. It's literally cone, right? So it requires 3D volumetric information of the patient. Okay, so typically one single rotation is enough to acquire the 3D volume, right? So as compared to our, CT sim, if you still remember, okay, the beam is fan, right? So X-ray is coming from the source, and it is fan shape, and the thickness is actually a lot thinner, right? That's why the couch has to move in and out of this fan beam. So inherently, cone beam CT has poor image. Cone beam CBCT has, how can I say, it's a lot noisier, right? Noisy than regular CT. Why is that? Because there's a scattering, the scatter effect. Okay, so all these X-rays, it bounces around and it captured. It's a lot noisier. Whereas in CBCT, it's well collimated. Okay, so it acquires slice by slice almost. So that's the difference. But it is very convenient because with the one rotation, you can acquire 3D volume. Okay. So as I mentioned, so the X-ray source is here. Then kilovoltage imaging panel is opened up. Okay. And then this is actually MV source. Okay. The variant machine, it cannot acquire MV CT. It's only cone beam CT is using the kilovoltage. Okay. So we can use kilovoltage source and panel not only for actually CBCT, right? We can acquire a 2D image. It can be used also a fluoroscopic mode. All right. So this is the image where you can see is actually the X-ray source side. We have two different filter. Okay, so we call it fan. Okay, so full fan and half fan. It is actually two different type of the bow tie filter. Okay, so this is full fan on your left, and you have half fan on your right. So this can be actually removed. Okay, so replaceable. Okay, you can just rotate this knob and unlock it, and then take it off, then put it back. So with the full fan, you are acquiring smaller field of view. Okay, so we use this for the brain, head and neck, and the detector is centered. Okay, detector. Okay, so this is detector, and this is X-ray source, and the yellow thing is bow tie filter. Okay, it looks like bow tie, right? The X-ray source is here, and then you acquire image. Okay, so the center of the panel, and then it is actually aligned with the X-ray source. All right. So for full fan, you do not need one full rotation of the gantry. Okay, you only need about 200 degree rotation of the gantry to acquire 3D volume. Okay, but we have another option is a half fan. Half fan is actually used for a larger field of view, such as lung, liver, pelvis. So in this setup, if you mode up it with this full fan, half fan, the detection panel will move, okay, will slide to the side to capture this half of the patient, okay, and it is actually using this half fan. That's why we call it half fan. And then it'll rotate around, then it acquires the other side of patient anatomy. So it requires a full 360 rotation, and then the image quality is actually inferior to full fan, but what is good about it, it has larger field of view. Okay, let's talk about the imaging dose from the kilovoltage cone beam CT. Okay, so standard dose ahead, it's about 1 centigrade, 1 millisievert or less. Um, and then pelvis scan, it's about several centigrade, okay, which is actually more like equivalent to the CT, regular CT sim. Okay. But one thing interesting you may want to actually notice is where the dose is being deposited. Okay, so this is actually a cone beam CT of the head, and then this is Monte Carlo simulation. So in this example, the the X-ray source for the cone beam CT swept behind patient back. Okay, so if you recall, um, this full fan mode, you need 200-degree rotation, right? So you can control where the X-ray source actually starts. So you need like 200-degree, right, of rotation. So in this example, because the X-ray source is rotated behind the patient head, um, most of those is deposited in periphery of the skull. Okay, whereas we can spare a lot of those in the front. So if you are concerned about lens dose, for example, you can design your image acquisition in a way that you sweep through behind, like patient posterior side of the patient. So tomotherapy unit has this somewhat unique mega voltage CT. Okay, so it means tomotherapy itself, unit itself looks like CT scanner, right? So it has a CT-like entry, and then it has this 6 MV linear accelerator. This whole thing you see is a linear accelerator. And this same linear accelerator that used for treating can be also used for megavoltage CT imaging. So in that imaging acquisition mode, the energy of the photon beam will be reduced to like about half. And then there's actually a detector array here. I'm not sure you can see it very well. These are detector array. Okay, the xenon gas detector array is attached. Okay, so as the patient couch proceed, the gantry rotates and it acquires megavoltage CT of the patient. Okay. So just for your comparison, on your left, you have regular diagnostic or CT sim quality CT, and on your right, you have tomotherapy megavoltage CT. So one thing you notice is the image is more like grainier. Okay. And then the other thing is you might call it advantage, significantly reduced image artifact from this, fiducial, right, gold markers. So these are metal, so in kilovoltage diagnostic style CT, you see this streak artifact. However, in megavoltage CT, because it's more voltage range, you have less of photoelectric effect, and you have this nice image of metal implant. There's another example of MVCT versus KVCT. In kilovoltage CT, as we learned, you have some artifact, right, from the dental filling, and you do not have that at all in megavoltage CT. So in a CyberKnife system, which we do not have in our department, it has somewhat unique imaging system. Okay, so as I mentioned here, so you have this in-floor X-ray imaging. So this is X-ray source. You have two tube, and patient is sitting here, and this two is actually X-ray imaging panel. Okay, so the X-ray source will come from the ceiling, then across the patient, then come down. Okay, so it's not something like this, right? And then this. Yeah. So the advantage of this system, well, disadvantage of this system is it's not a volumetric acquisition, right? But it's only 2D snapshots. But it can be acquired in a very short period of time, so it can be used in, multiple times throughout the treatment to verify patient position or like tumor location. Okay. So the other thing unique about this system is it has a infrared camera here. okay, that monitors this special patient vest. Okay, patient is wearing this with a bunch of reflected, actually infrared reflective balls, or like some sort of like a reflector, and then this camera monitors this motion, right? So it's, for example, it's patient breathing motion, okay, and then that can be, you know, that feedback can go back to the system, and this whole gantry can breathe, like move with the patient. Okay, so it's a unique, clever system, but you know, whole treatment is taking so long. That's why it's not as popular. All right. So once we either using cone beam CT or, you know, from KV shots, once you get the, you know, given day's patient position or the tumor position, you can use that information to move the couch, right? So typically we use like three-dimensional direction, vertical, longitudinal, lateral. But a more modern system has 6 degrees of freedom, right? So not only you correct for the vertical, longitudinal, lateral, you have this pitch, yaw, roll. We call it actually rotation instead of yaw. We have roll, pitch, and couch rotation, right? So that can be corrected, which is nice for, like, you know, SRS and small target SBRT. All right, so that's all I have actually. I want to summarize all we learned with these 3 slides. Okay, so this is summary. What every RTT students should know about imaging. Okay, so first you have to understand how the X-ray is produced, right? So the key term here is Bremsstrahlung, right? So you have to understand the X-ray tube, and you have to understand the key mechanism, okay, the Bremsstrahlung. Okay, and then you have to understand what are the different imaging modalities available in radiation therapy treatment planning, right? So CT, PET, MRI. Then you have to understand the film radiography. Okay, we talked about this characteristic curve, and then we talked about optical density and CT simulator. You know, you have to understand this, you know, history. Okay, what is our current CT scanner? It is 6th generation helical scanner, right? And you have to understand house field unit. What is the house field unit for water? Yes, it's 0, right, by definition. And then you have to understand the CT image artifacts. So we talked about, you know, partial volume artifact, the metal artifact, and so forth. In PET CT scan, you have to understand the principle. Okay, so PET provides something that CT cannot provide, right? So it's metabolic information. That is what PET is providing. And what is the isotopes that we use? You know, you have to know the FDG, and then this concept of coincidence detection system. Okay, we're taking advantage of this 180, almost 180 degree apart annihilation photons, and then what are the image artifact from the PET, right? So we talked about this attenuation correction, and then we talked about the image blurring, right, and so forth. And ultrasound, you know, what are the typical ultrasound frequency, you know, which frequency gives more in-depth, deeper imaging, and which frequency will give you shallower imaging, you know, and with a higher image resolution. And MRI, we talked about basic principle of MRI, and we learned about T1 weighted and T2 weighted. So you should be able to tell by just looking at MRI, you know, is it T1 weighted or T2 weighted? And then we learned about the list of what's currently commercially available in-room imaging, and then, you know, how cone beam CT works and how portal imaging works. So that's all I have. So I hope you guys enjoyed my lecture series. If you have any question, always feel free to reach out to me. Okay, thank you. Bye.